So now we move on to section 10.4, which is titled Divergence and Integral Test. Now here is a paragraph from the textbook which explains where we are going quite well. So I'm going to read a little bit of it. So it says, with geometric series and telescoping series, the sequence of partial sums can be found, and its limit can be evaluated when exists. So we saw that earlier with the first example, and then in the case of telescoping series, that we were lucky enough to be able to find Sn. Unfortunately, it is difficult or impossible to find an explicit formula for the sequence of partial sums for most finite series. Therefore, it is difficult to obtain the exact value for most convergent series. So in light of these observations, we now shift our focus and ask a simple yes or no question. So given an infinite series, does it converge? If the answer is no, the series diverges and there is no more questions to ask. If the answer is yes, then the series converges, and then it may be possible to find or estimate its value. So the first thing we study is divergence test. So what that means is this test is exclusively to find if a series diverges. Now it's a little tricky, and I'll go slow and explain in different ways, but you have to really pay attention to this. So given any series, the first thing we can start with is to apply the divergence test. It is easiest test and can decide if a series diverges. So this is what the test says. It's explained in two ways. So both these statements are equivalent. So the first one says if a series converges, then the limit of the sequence of the terms is 0. So but this is not useful. The reason it's not useful is because its hypothesis is that a series converges. Now, if we know a series converges, why bother anymore? So this is useless. But its equivalent version, and some of you may know this is the contrapositive if you have taken some other math courses like Math 2000, you may know the term contrapositive. So basically this is equivalent, and what this says is something very interesting. It says if the limit of ak is not 0, then the series diverges. So the useful version of it is, so remember our series is sum of ak. Now we are going to just take ak as a sequence. So from here we can just pick up the sequence, and then we can find the limit of this sequence. Now remember, this can be done from our previous knowledge. So in the previous section we learned how to find limits of sequences. So we can find this. Now if this turns out to be not 0, then we know for sure that the series diverges. So this is what it says. Now here is the temptation. And a lot of students fall for it. So one would think, obviously, which is not right, but you may think that if I take the limit k going to infinity of ak, and suppose it turns out to be 0, so the question is, does that mean that the series converges? Does it? The answer is no. It's very tempting, but just because the sequence ak goes to 0 does not mean that the series converges. So let me repeat. If you find the limit of this sequence ak, that means just simply the numbers of the series, and if the limit is 0, you cannot conclude that the series converges. In fact, what this means is we know nothing. So we cannot say it diverges, because for divergence the limit should not be 0, and we cannot say it converges. So basically what that means is it's useless. This test did not tell you anything. Okay, let's look at some examples and make sure we understand how to use this result. So here is my series k squared plus 1 over k minus 1. So first thing is, let's pull out ak. So ak is k squared plus 1 divided by k minus 1. So I'm looking at it as if it's a sequence. So now I have to find limit k going to infinity of this. Now this is the kind of stuff that you have done again in Calc 1. So if you want to find the limit k going to infinity, what you can do is you can divide the numerator by k, and you can divide the denominator by k. Be careful with this algebra. So what we get, so k squared plus 1 divided by k gives me k plus 1 over k, and in the denominator I get 1 minus 1 over k. So now as k goes to infinity, what do I have? Infinity plus 1 over k is 0 divided by 1 minus 0. So which means this is infinity. Okay, so therefore my limit k going to infinity of ak is not equal to 0. It's infinity, in fact. So therefore the theorem says that this series diverges. Okay, now let's look at the next one. Now this series you have seen before. Oh, by the way, this series has a name. It's called harmonic series. We also know, well, we really don't know, but at least I had told you that this particular series diverges. Remember the very first time when I was talking about series, we had this example and this example. So I had mentioned that this one we know diverges. Okay, so let's try the divergence test. So what is my ak? So ak is 1 over k. So now I can take limit k going to infinity of 1 over k, and that is 0. So now one would think that what's the conclusion? Well, you have to go back here. If the limit of ak is 0, that means no conclusion. We know nothing. So therefore your answer or is no conclusion. And that will happen in series many times. You would use a test and you will come to no conclusion. So one must be thinking that, hey, I know that this series diverges. Why didn't this test tell me it diverges? Well, every test may not come to the conclusion. So there are other ways by which we will see that this series diverges. Okay, let's go to the next one. Here, ak is 1 over k squared. Oh, by the way, we know that this converges. Remember we talked about the fact that the sum is pi squared over 6. So we know that this series converges. So let's see what we get. Limit k going to infinity, 1 over k squared is 0. So again, we have a situation where we know that the series converges, but there is no conclusion. The point that I'm trying to make here is that just because AKs go to 0, that means the limit of AK is 0, does not mean that the series converges. So some of you will try to get away by saying this kind of stuff, but please remember this is not true. I mean, if you think about it, if it was that simple, why there's nothing much to really study, because finding a limit of AK is easy. And if it was that easy that you can see the limit equals 0, then we could come to many conclusions. So please don't make this mistake. Okay, so I'm repeating again. This test cannot be used to show convergence. And that is something that many students make all the time. Okay, so let's go on to the first test for convergence. So this is called the integral test. Now this is the very first test we are learning to check if a given series converges or not. Now it is a very versatile test. It's a very powerful test, but it is an overkill. In other words, there are many more tests that you're going to see which may be easier to use for the problem at hand. So you should not always just say, okay, I can just use integral test. One would normally use it when these kind of things happen. For example, if the terms of the series have transcendental functions, or when other tests do not work. And we are going to see many more tests coming up in the next few sections. So what is the integral test saying? It says that suppose f is a function, positive, continuous, decreasing function, so that ak is f of k. So that means basically this f of k is that generating function that we saw when we were studying sequences. Then the series that we are given and the improper integral. So what we do is we find this improper integral. Notice that the limit is infinity, from 1 to infinity, fx dx. So we find this. Then either both converge or both diverge. So that means that if this improper integral converges, then the series converges. If this guy diverges, then the series diverges. So that means they go together. In case of convergence, the value of the integral is not equal to the value of the series. So there's a